Hi friends, today we are going to start finish I should say, section 5.1, day 2, still working on those trig identities. So go ahead and take out a notebook, and here we go. There's only one new set of identities that we have not covered yet, and they are our odd and even identities. So our odd even identities, if you remember way back earlier in the semester, we talked about odd functions and we talked about even functions. I'm going to go to another picture real quick. You don't need to write this down, but I just want to explain it so you can kind of see what this is talking about. If we talk about our sine function, if you remember our sine function started at 0, it went up to 1 and down to -1, and it kind of looked like this right here. That was my sine. Our cosine function started up here at the top of 1, and then it went down to the -1 and back. Okay, so this is our cosine function. One of these functions is considered to be an even function, and one of these functions is considered to be an odd. So if we think back to when we had like x squared, and we said, yeah, that was an even function. When we defined even functions before, we said even functions were ones that were symmetric about my y-axis. Here's my y-axis. Meaning that if I were to take this and I were to flip it, let's see, left to right, it should look like the exact same function. So even functions are ones that we can flip over our y-axis and they stay the same, which means that this one right here would be an even function. If I were to take that entire graph and if I were to flip it left to right, it still looks like the exact same graph. Now a sine function, an odd function was like if I had the graph at y equals x cubed, that's a little 3 right there. Our cubic functions, I'm going to not draw just the basic cubic, I'm going to draw a cubic in general. Looks kind of like this. And those cubic ones, we should be able to take it and rotate it around the origin. And if it truly was an odd function, I should be able to turn it all the way around, and it should end up looking like the exact same thing. If I were to do that with my sine function right here, if I were to take it and rotate it all the way around, it should end up looking like the original right there. So sine is an odd. So when I give you these even and odd identities, it's going off of that fact that the cosine function, because it's symmetric around my y-axis, it has all the properties of even functions. And the sine function, because I can rotate it around, it has all the properties of odd functions. When we proved even before, because back in, I believe, chapter 2, we had to prove if something was even or odd, it just said that f of x equals f of negative x. And when we proved odd, we said f of negative x equals a negative f of x. Okay, here's what I actually want you to write down now. So when we have these even odd identities, our even identities, I'm just going to start with the ones that are even. Our even identities say this: if you have cosine of negative x, that would be the exact same thing as cosine of x. That's all that even really meant. If you had it with a negative, that's going to be equivalent as if you completely got rid of the negative. So how that's going to help us with our proofs or our identities that we're going to be doing is if you ever end up with a cosine with a negative, you can just basically forget about that negative as long as it's cosine, because cosine is an even function. The only other trig identity or trig function that is even would be secant, because if you remember, secant is the reciprocal of cosine. So if you ever have a secant of a negative x, you can say that that is secant of x. So for those two and those two alone, if you have a negative on the inside, it just goes away. For the odd functions, which is the remaining of our trig functions, if you have a negative on the inside, we have a negative on the inside, that meant the same thing as just taking that negative and putting it on the outside. So this is going to equal a negative sine of x. The reciprocal of sine would be cosecant. So if I have a cosecant of a negative x, that's going to equal a negative cosecant of x. It also is true for tangent. That would give me a negative tangent of x. And it's also true for cotangent. That'd give me a negative cotangent of x. Now, some of our other trig identities, I told you, these will work if it is squared, if it's cubed, if it's etc. It's kind of true for these. If you happen to have like a sine squared of a negative x, remember that really means sine of negative x times another sine of negative x. Don't write this down, just kind of follow along here. Which means that I can't just say that I'm going to take one negative out, because here it says that's going to equal a negative sine of x. That means for this first one of the ones being squared, that first one is going to equal a negative sine of x. But then the second one is also going to be a negative sine of x. And a negative times a negative would be a positive, and sine times sine would be sine squared. So if they raise any of these to powers, you have to be really careful for the odd functions specifically. For these ones, if you raise it to a power, like let's say you raise it to the second power, then you would have to take two negative signs out, meaning a negative times negative, and it will end up being a positive sine squared. If you had three, so if it was sine cubed of negative x, you'd have to take three negatives out, and a negative times a negative times a negative would then still be negative. So you do absolutely have to pay attention to the exponents for these ones. They will still work, you can still do them, but you just have to make sure you take that many negatives out for those odd functions. Okay, we're going to try a bunch of examples now. So here's my first example. It's going to say if the cosine of theta equals 0.34, I want us to find the sine of theta minus pi over 2. Now, a lot of people will look at this one and they'll say, oh, well, that's easy because if it's that, that's our cofunction identities. It's not actually quite our cofunction identities. Our cofunction identities went pi over 2 minus theta. So you might say, well, let's just switch the order. But if I switch the order, I would have this, sine of negative pi over 2 plus theta, because the negative is with the pi over 2 and the theta is positive. So then what I want you to do is factor out a negative. So I take a negative out of the pi over 2 and I take a negative out of the theta, so I get this. So now what I see is I can use my even odd identities, because my even odd identity says this. I have sine of a negative quantity. That would give me a negative sine of that quantity. And then my cofunction identity, which we talked about earlier, is going to say that sine of pi over 2 minus theta is really cosine of theta. So to answer this one, I need to take the opposite of cosine of theta. And at the very beginning, they said a positive cosine of theta is 0.34. So this one would have to equal a negative 0.34. Okay. So to use those cofunction identities, you absolutely have to have it going in the correct order. If they're not in the correct order, then you can use your even odd identity to kind of switch things around so that we can actually do this. So here's my next one. I've got sine cubed of x plus cosine squared of x, and they want us to simplify. For this one, and what we're going to start to see a lot more in today's problems, is they're going to basically be asking you, not all of them, but they're going to ask you to start factoring with these. If this is one term, and all of this is a second term because of that plus sign right there, I'm going to look to say, what do they have in common? And sometimes people see it and sometimes people don't. If you don't see it, you can also think of it in another terms of this problem, an easier problem. I could think of this as I have something cubed plus that same something times something else, because now it's cosine, squared. Between those two green terms, you would hopefully say, well, they both have an x in common. Well, between both of the terms that I have underlined here, I could say, well, they both have a sine of x in common. So what I'm going to do is I'm going to factor out that sine of x. I'm going to undo the distributive property. If I take one sine out of sine cubed, that'll leave me with sine squared of x. And if I take one sine out of the sine cosine squared, that sine is completely gone because I'm factoring it out, which leaves me with cosine squared of x. And if I have that, hopefully you notice, oh, I see two trig identities that are being squared, sine squared plus cosine squared. That's the Pythagorean identity. That entire quantity is just 1. And sine of x times 1 would just simplify all the way down to sine of x. Okay. So look at each individual term and factor out whatever they have in common in that particular case. So our next one is, I've got secant of x plus 1 times secant of x minus 1 all over sine squared of x. For this one, I see 1s in there, but I don't see any trig identity squared in that top of that fraction. And in fact, I see a secant plus 1 and a secant minus 1. We are going to see this a lot throughout this chapter where they are just different, like they are different by that one negative sign. When you see that, hopefully that you recognize that as a difference of two squares pattern, which tells me when I see something like that where they're almost identical, it's just that their signs are different, I want you to FOIL that out. The first step in the FOIL is going to kind of be a doozy, but then after that, there should be a really easy substitution for us to do. So if I FOIL this out, that would be taking a secant times a secant, and they'll give me secant squared. This is going to give me a minus secant of x. This is going to give me a plus secant of x, and that's going to give me a minus 1. All of this is still over sine squared. And here's what's nice about that. A negative secant plus secant, those cancel. So I'm left with a secant squared of x minus 1. I have a trig identity being squared, and I have a minus 1. That tells me that there's probably a Pythagorean identity. So I'm going to just write it down for right now. And I'm going to look at my Pythagorean identities. And there is one that says secant squared of x minus 1. That would be tangent squared. So right now I've got tangent squared over sine squared. So it already is looking simpler. But I would say at this point I kind of get stuck. If I get stuck, I'm going to switch everything to sines and cosines. Here's what I know. Tangent is really sine squared over cosine squared. I'm going to write it this way. That tangent that I just wrote down there is being divided by sine squared. The reason why I like to write it like that is because I am going to write this in red. I don't like to have a fraction sine squared over cosine squared, and then it's within another fraction. I think that looks confusing. So since all I'm doing is dividing by sine squared, I'm going to write it as literally divide by sine squared. And the reason why that helps me is because then my brain can process that and say, well, if I'm dividing two fractions, I just need to multiply by this one's reciprocal. And then I can say the sine squared and the sine squared cancel. That'd leave me with a 1 over a cosine squared, and that is secant squared. So all of that would simplify down to secant squared. Okay, let's try another one. So we are going to keep simplifying. We're going to have cosine of x minus 1 minus sine of x minus sine of x over cosine of x. Okay, so here's where we have to remember we can't let the math police come out after us. So math police would say that if you are adding or subtracting two fractions, you absolutely have to have a common denominator. Right now I do not have a common denominator. So I'm going to say, well, there's not an easy way to get a common denominator. Besides, I'm going to just multiply the top and the bottom of this first fraction by the denominator of the other one, so by cosine. And I'm going to multiply the top and the bottom of this second fraction by the denominator of this first fraction, because that should give me one fraction. I'm not going to multiply out the denominator, so that's be a cosine x times 1 minus sine. You absolutely could, but I've done this problem enough that I know in the future my hope is probably going to be to try and factor it so that things can cancel and I can simplify. So I'm going to leave that. However, the top there might be like terms, so I am going to multiply that out. In the top, I will be taking a cosine times a cosine, which would give me cosine squared. And here, be careful, when you multiply out this sign, make sure you're multiplying out a negative sign. So negative sine times 1 would be a negative sine. And a negative sign times a negative sign would be a positive sign squared. Okay, now when you add or subtract, you can add or subtract in any order that you wish, meaning the top of this fraction, I'm just adding and subtracting terms. I have a cosine squared here, and I'm attempting to add a sine squared to it right there, and I know that sine squared plus cosine squared really just equals 1. I still have to write that minus sine of x because I didn't do anything with that. But those two green circles that those two terms I circled in green, those combined to just give me 1. In my denominator, I've got this, and then good news. As soon as you have a quantity, so a 1 minus sign, I can only cancel it if I have the exact same quantity in my denominator, which I do. I can cancel this entire thing right here with this entire thing right there, which leaves me with a 1 over cosine of x, which tells me that this one simplifies all the way down to just a secant of x. Okay, so those are our simplifying ones. Then there's one new concept that we're going to be doing now starting today. We're going to start factoring with these trig ones. Example 5 and example 6, I've got 2 examples left. I apologize for the long notes today, but we're going to find all values of x in the interval from 0 to 2 pi. That solve, that is supposed to say a pi. It doesn't really look like a pi. Let me fix that so you can actually read my handwriting. That solve this equation. Cosine cubed of x over sine of x equals cotangent of x. Okay, so for this one, a lot of times people start this and they say, I thought you said we're factoring. We are, just trust me here. So here's what I'm going to do first. I'm going to say, well, cotangent of x. That's really, I can change that if I'm not sure where to start. I can start by saying this side equals cotangent would be cosine of x over sine of x. And then what we can do from there is, we can do a couple different things, but what I would do is I would say, well, let's multiply both sides by a sine of x. Let's just get rid of these fractions. This cancels, this cancels. That gives me cosine cubed of x equals cosine of x. And then what I'm going to do is I'm going to say, well, I'm not still sure what to do, so I'm going to set it equal to 0, because you mentioned we might need to try to factor, and normally when we try to factor, we want to have the entire thing set equal to 0. Okay. I have 2 terms here. You cannot actually subtract those. That would be like saying you're taking x cubed minus x, and the math police would come out to you, because I have a lot of people who try to tell me that it's that. A cubed minus a linear term is not a quadratic. So here, cosine cubed minus cosine is not cosine squared. But what you are noticing is they both have that cosine in common. So let's factor out what they have in common. They have that cosine in common. That will leave me with a cosine squared of x. If I take a cosine out of a cosine, that would just be a 1. And now that it's in factored form, I can set each piece equal to 0, and I can try to solve. So I'm going to set this piece equal to 0. I'm going to set the cosine squared x minus 1 equal to 0, and I'm going to try to solve that. I'm going to start with this first piece on the left here. This one's a little bit easier. It's really saying in the interval from 0 to 2 pi. So look at the full unit circle. If you have your unit circle from last chapter, take that out. I want to know all the places that my cosine equals 0. Cosine, remember, was my x value. My x value is 0 right here, and my x value is 0 right there. That top one would be at pi over 2, and that bottom one would be at 3 pi over 2. Now, I don't want to go down to those, because the original interval they gave me was from 0 to 2 pi, so they're telling us just find your positive one. And then this one over here, I want to try and get the cosine by itself, so I'm going to add 1 to both sides. that'd give me a cosine squared equals 1. And this is really like something squared equals 1. Well, to get rid of the squared, I'd have to take the square root, and the square root of cosine squared would just be cosine. The square root of 1 would be plus or minus 1. So I'm going to look back to my unit circle, and I'm going to try and find all the places that my cosine is a positive 1 or negative 1. That would be right here and right here. That first one, I want to include 0, but don't include 2 pi. So I want to say 0. And then the second one would be a pi. Now here's the only catch. Everything we've done so far has been perfect. But look back at your original problem. If your original problem had fractions, obviously that's a fraction, but I would even say that this has a hidden fraction, because notice right here, cotangent could really be written as cosine over sine. So because of that, I have to make sure that of all the answers I have, none of them are causing me to have a denominator that equals 0. So I just have to check, do any of those 4 numbers we just wrote down happen to have force your sine to equal 0? Because if my sine equals 0, I'd say, no, that's an error. I can't divide by 0. So at this first point right here, my cosine was 1, but my sine was 0. This right here works for the cosine portion, but because I have to look back at the original problem, if I put 0 in there, that would cause me to divide by 0, and I can't divide by 0. This point right here, my sine, my y value was 1. I can divide by 1, that's okay. So that tells me that this point checks out. This point right here, when my cosine was negative 1, my y value was 0. Once again, my sine is 0. I can't do that because that causes me to divide by 0. And then this final one right here, my y value, my sine would be negative 1. I can divide by negative 1 and not get an error on my calculator, so that one works. So the only answer I want for this one would be pi over 2 and 3 pi over 2. Okay. Last problem. Thank you for bearing with me on all these notes. We're going to find all the solutions again. Oh, whoops. Let me write a little bit nicer. All values of x in the interval 0 to 2 pi that solve this equation. 2 sine squared of x plus sine of x equals 1. Okay, for this one, here's what we want to do. This one does not have any fractions, so I can't just multiply and get going from there. Most of these, not all, but a lot of these problems you're going to have to try to factor, and if you're going to try to factor, you want to set it equal to 0. So I'm going to start this by subtracting 1. That gives me 2 sine squared of x plus sine of x minus 1 equals 0. Now, unlike the 2 factoring ones we've done so far, there's not any GCF. There's nothing that these terms have in common. Some people might say, well, they have a sign. There's 1, 2, 3 terms. The first 2 terms absolutely have a sign. That minus 1 does not have a sign. So I cannot undo the distributive property in order to factor this one. What I can do is I can think of it like this. This is really like I have this problem. 2 times something squared plus that something minus 1. And if I asked you to factor this, hopefully you'd say, okay, well, I think I can do that. 2x squared would be a 2x times an x. The only way to multiply to get 1 would be 1 times 1. I need it to be a negative 1, which means one of those is going to end up being negative. If I try to FOIL this out, that will give me a 2x. This will give me a 1x. And one of those needs to be negative, and I want to end up with a positive x right there. So that tells me I want this to be positive, so I have a positive 2x. I want this to be negative, so I have a negative 1x, because 2x minus 1x gives me that 1 in the middle there. Remember this right here, okay? If I try to factor this sine one, I'm going to do basically the exact same thing. I'm going to say 2 sine squared is either 2 sine of x, and it has to be times another sine of x, because when I FOIL that out, that gives me 2 sine squared of x. Notice I have a 2 times something right here. I have a 2 times something right here. I have a sign right here. I've got that 1 something right there. The only way I can split up a 1 would be 1 and 1. It's a -1, just like that last green one was a -1. And I'm going to keep the signs the same. And then the nice part about these is as you factor this out, if you're not sure if it works, do a quick FOIL in your head. You don't have to show all your steps for your FOIL, but if I FOIL this, that for sure gives me my 2 sine squared. That gives me plus 2 sine of x minus 1 sine of x. That would give me 1 sine of x. And that gives me -1. So yep, that absolutely does factor to 2 sine x minus 1 times sine x plus 1. It's just like this, 2 times x minus 1 and x plus 1. Okay, now that I've got it factored, I use my zero product property to say 2 sine x minus 1 equals 0 or sine x plus 1 equals 0. For this first one, I'm going to add 1 to both sides. That gives me 2 sine of x equals 1. I'm going to divide everything by 2. And that gives me sine of x equals 1/2. I'm going to come back to that in just a second. For this one, I'm going to subtract 1 from both sides. I'm just trying to get the trig function by itself, so that gives me sine of x equals -1. This first one is really saying where on my unit circle are all of my y values that have a positive 1/2. Well, a positive y value would be up in either quadrant 1 or quadrant 2. Sine of 1/2, if you look on your unit circle, that should be right here at pi over 6 or right here at 5 pi over 6. This next one is saying where is my sine -1? Sine, remember, is my y value. My y value is -1. Down here, there's only one place, and that'd be at 3 pi over 2. Now, like that last one, if I check my original problem, I'm going to look, are there any fractions? Well, no, there's no fractions throughout here. And then I'm going to ask myself, are there any hidden fractions, like that cotangent was really a hidden fraction because cotangent is cosine over sine? Nope, sine is not a hidden fraction. Some people might say, well, it's 1 over cosecant. When I look for those hidden fractions, I'm looking to see, is there any way that I could rewrite those in terms of sines and cosines and have a fraction? Excuse me. So I would say, nope, there are no hidden fractions, which means there are no errors. So I get this right here. I just want to say one last thing. There might be times when they say find all the values and they don't give you an interval. If they don't give you an interval, then basically they're saying it could be at right here, that first one at pi over 6, but it could also be a full circle and at pi over 6, or it could be 2 full circles in there or 3 full circles in there. Remember, 1 full circle would be 2 pi. So if they just say find every solution and they don't give you an interval, we'd have to change our answer to be this. Pi over 6 plus 2 pi n. N means go around that circle as many times as you want. Same with this. I could say 5 pi over 6 plus 2 pi n. If they didn't give me an interval, then that would mean go around that circle as many times as you want, because that n is the number of times you're going around the circle. And then similarly, I could say this plus 2 pi n. I wouldn't stress too much about that. There might be a few problems in your homework assignment, but on our future tests, I'm not going to give you any like that. So don't stress too much. I just wanted you to see what that would look like if you were checking your work at the back of the book. Okay, that is everything. Have a great day.